So let's have a look now at how we can use pointers and some functions and procedures from the programming language in order to work with dynamic data on the heap. As we've seen, pointers can be used to refer to locations in memory. That location doesn't just have to be on the stack where we point to a value inside a variable that we already created. We can also use it to point to values on the heap and put something on the heap for us to access. We can picture this as the pointer inside our local variable having a value where the location in memory is actually on the heap. That's really all we're doing. We can follow the pointer to get us from the stack into the heap so that we can read the values here and potentially access multiple values. You can have a pointer referring to an array of values. And the language, at least with C++, makes it easy to interact with a pointer as if it were an array. Let's have a look at some of the system functions to allocate space on the heap. Allocating space allows you to create a space on the heap, and we can use the pointer to refer to that space. In C++, we use this malloc function. What does that stand for? M is for memory, alloc is for allocation. So allocate some memory. We need to tell it how big the memory is that we want. In this case here, size of int is a function that's provided for us that gives us the size of a certain data type. So you can pass in a type here, and you say, I want the size of that type. And depending on how big that type is, that's how much memory you get. Now malloc is used in general, so it could return a pointer to anything. This typecast here is a C typecast, and it allows us to say that what I'm getting back from malloc is a pointer to an integer. And you've got to make sure that that is actually valid. And in this case, because it is the size of an integer, we can pretend that it is a pointer to an integer. We can indicate it's a pointer to an integer. So let's have a go at that in our example project. So here was the code I had so far, where we're just pointing to the different variables that we've allocated. Now, what we can do here is I can say p equals, the way I would write it is malloc, size of, and we pass in my type. Once I've done that, I would come back and put in this here. That's just to stop the compiler complaining. Now, one thing you would have to do in order to access this is hash include the C standard library. The C standard library includes this malloc function, size of, etc. All of the things to manipulate memory is in the standard library. Once we've done that, we can actually print out the value that's there. Even though we haven't given it a value, it will be whatever happened to be there previously. If I change the value, we can then print that value out again. We can see when I run this, we allocate our space on the heap. That's where that occurred. And when we follow it, it had the value 0 to start with by chance. And we then assigned it the value 42. So when we followed the pointer again, we accessed the value 42. But that value came from the heap. There isn't a variable where that value is actually stored. It's stored on the heap and only accessible by this pointer. Now, one thing we should do is make sure that we free the space that we use once we've finished with it. The way we would do this is just to call free and the pointer and assign it to nil. Now, I don't have to worry that I ran that program and didn't free that memory. The program terminated. When it terminates, all of the memory that it was allocated is freed. But if your program runs for a long time, such as a web server or a database server, then forgetting to free pointers would mean that system resources are being used for a very long time. That's where the problems really start to occur. So here we go. I free the pointer and nil it. Running it does exactly the same as before, but we've deallocated that memory that we created there or allocated there. Now, we can allocate space for more than one value at a time. What I allocated space for then was one integer value. But if I want to, I could just ask for more than one value. So here I can say that my pointer I want to be assigned the space big enough to store 4 integer values. Now, because this is an integer pointer, we'll be able to access each of those one at a time. And you can treat the pointer p just like an array. So if I did that here, I can say p equals malloc, the size of an int times 4, and we then have that available as an array, and I can iterate over that or accessing each of those values. Now, just like a standard array, it doesn't remember its size, so I would have to use something to remember that. So you could possibly create a struct which had a pointer and the size inside it. And that's effectively what a vector is doing for us. It's good because it's a lot of hassle to do this manually, But if we wanted to do that, we could now build that ourselves. Once you've created a space in RAM, you can also change the size of that. And that would be done using a call to realloc. Realloc obviously standing for reallocate. Now that gets past the pointer that you want to reallocate, the new size of that pointer, and it returns potentially a different pointer altogether. Now this is the challenging part. You've got to do this in sort of 2 steps. Why? If I ask for RAM, it might not be possible to increase the size. The next bit of RAM might already be used by something else. In which case, realloc finds somewhere else in memory entirely, puts your value there, copies all of the old data across, and deletes the old space. When that happens, we need to make sure that we reallocate the pointer p. Now, what can also happen is that there isn't enough space anywhere in memory at all. When that occurs, it doesn't change p. It leaves p referring to what it was pointing to before, and all of that memory is still allocated. What it returns then is null. So that's what this check is doing here. If the pointer we got back is not nothing, so the null pointer indicates that it points to nowhere in memory. It's actually the value 0, and it's special to mean not a valid pointer, effectively, null or nothing. So if the pointer points to nothing, or if it doesn't point to nothing, then assign p to be the new pointer, because the new space has been allocated, and with that's worked successfully. If, however, the return value is null, we've run out of memory, and so we should probably look at freeing up some memory somehow. Our program's most likely going to crash in a second anyway. Now, any language that uses dynamic memory allocation will be using these features behind the scenes. It's just a matter now that we can start to play with them ourselves.